Swayam Prabha. Digital India. Educated India.
Hello and welcome to the discussion series on the production technology, theory and practice. My name is Dr. Shaunak Kumar Chaudhary. I am a professor in the Mechanical Engineering Department of IIT Kanpur, teaching here for the last 34 years. My specialization is manufacturing science in mechanical engineering. Apart from that, I also work on the unconventional machining, NC machines, manufacturing automation and so on. So, in this series of discussions, we will have 5 modules apart from the lab. So, the first module is the materials, engineering materials and their properties we will discuss. Next module will be on machining, on the conventional machining. So, there we will discuss the theoretical background on the machining processes. We will look into various practical machining aspects. We will see how some of the very simple simulations or mathematical models are built up. We will see the thermal aspect of machining, stress, strain, how the chips are removed, what is the tool, how the tool wears out and so on. So, there are different aspects, basically many things are known to you, but we will discuss the reasoning mostly, that why things happen that way. For example, why the chip is hot and so on. Now, the third module will be unconventional machining processes. There we will discuss those unconventional processes or non-traditional processes, as they are also known as electrochemical machining, abrasive jet machining, electro discharge machining, plasma arc, electron beam machining and so on, and we will see how these processes work and what is the principle of material removal in each of these processes, what is the kind of energy each of the processes used, and why they are called as unconventional machining or non-traditional machining, what is their use, where it is used and so on. Third module that we will discuss will be numerically controlled machines. So, we will discuss what is the difference between the conventional machines, turning lathe, milling, drilling machine and the numerically controlled or computer numerically controlled machines. Then the next module we will discuss about the metrology. We will show you different kind of tools, different kind of methods that are used for measuring. Now, you know the metrology is the science of measurement. So, how these measurements take place, and you understand that without that our production is incomplete, because we have to know whether we are making the right thing. So, the measurement is a very important phenomenon, and we will discuss that in details. Our sixth module will be the lab module. So, in the lab module we will mostly see the conventional machining section, along with the fitting and drilling, some portion of the metrology, how these measurement tools look like, how they are used, and the second part will be the NC and CNC machines, numerically controlled and the computer numerically controlled machines. So, there most of the attention will be on the principle of working and how the part programming can be made. Okay. So, in theory also, when we will discuss the NC and the CNC machines, we will discuss these aspects, and in more details we will show you in the lab that how these things actually can be done in practice or actually are done in practice. So, these are the 5 modules and plus the lab as the 6th module. We will discuss throughout the discussion sessions of this course, which we have called as the production technology, theory and practice. So, the first module is the engineering materials and their properties, as you can see in this slide here. Now, materials overall can be subcategorized into the metals and non-metals. Okay. Now, in metal we have also the ferrous metals, mostly based on the ferrous, that is the basis is the ferrous, and there are materials where there is no ferrous. Okay. So, those are called the non-ferrous materials. Also there are non-metals, and in the non-metals we categorize ceramics, composites, plastics. So, they are non-metallic parts, non-metal materials, and both metals and non-metals are extensively used in the engineering practice. Okay. You understand that the ferrous and the non-ferrous metals, they are everywhere, like blanks are made, like tools are made. Okay. Now, in the non-metal, ceramics, for example, for metal cutting, the ceramics widely used for making the tools or getting the coating on the tools. Composites, they are the materials which are light materials, very hard materials, all right. So, for their properties also they are used very extensively these days, because they are also light than the metals. Then of course, the plastics, and you understand and you see all around us the plastics are there, and plastics are also used in the as the engineering material in engineering practice, because the plastics are also very light, and plastics have reasonably good properties which is different than the metal, which may not be as good as the metal for some of the engineering materials we are using. And these days of course, there are newer and newer plastic materials which are being invented, and those some of them are even substituting the metallic parts, because they are light, because they can be used in the automobiles, they can be used in the aircrafts, for example, the gears. Okay. You can see that there are these days there are gears made of the plastics. Of course, their life may not be as high as the metallic gears, but nevertheless they are used, because they can be made easily also, because their machinability is better than the metal, and so on. So, those things we will discuss. Now, let us discuss the ferrous metals first. Under the ferrous metal, the most popular is the cast iron, and the cast iron is the product which comes out of the blast furnace, that is the pig iron initially. Okay. So, the composition of the cast iron is about, composition of the pig iron is about 3 to 4% of carbon, 1.5 to 2.5% of manganese, 1 to 3% of silicon, and sulfur and phosphorus additionally. So, this is the product which comes out of the blast furnace, which is known as the pig iron. Now, when this is cast directly, the pig iron, when it is cast directly, that is known as the cast iron. So, it is composition wise it is the same. Okay. that is percentage of carbon will be more than 2%, as you understand that, because less than 2 will be the steel which we are coming in the discussion. Now, the properties of the cast iron are that they are good in compression, okay, but bad in the tension, they are very brittle. Okay. So, as you remember, the stress strain curve, for example, for the cast iron, if you see, then this is the stress and this is the strain. So, for the cast iron it goes just here up to this, and here it breaks at this point. It breaks because it is brittle, it cannot, it does not have this function, like you understand that this is for the mild steel, for example, okay, for the ductile material, and this is for the cast iron. Okay. Now for the brittle material, since they break here, they cannot withstand the yielding. So, beyond yielding it does not exist. So, therefore, here up to this it is the stress strain curve slope can be found out, and so on. And then for the mild steel, which is the ductile material, here the curve can goes further like this, and there are different kind of mild steels. So, depending on that the curve can be different. All right. So, but they are good in the compression, okay, and for that reason actually the cast iron is widely used. Okay. You know that the cast iron is used in the building material. Okay. So, to make it stronger, for example, the cast iron rods are inserted in the concrete slabs and so on. They are brittle. Now, the cast iron has a good corrosion resistance. Now, what happens is it corrodes readily under the atmospheric conditions, and then that can be used, or that is used as a protective film, okay, or protective layer. So, further this material will not be eroded, that is corroded, sorry, not be corroded. So, the corrosion happens at the top, it readily happens, and then after that it does not allow the corrosion to go in. Therefore, it is used in the water pipes. Okay. When the water pipes are made, and you know that a huge quantity of the water pipes are made. So, therefore, the cast iron required is too high, requirement of the cast iron. Good vibration damping capacity, okay, because as we said that it has a good these are good in compression. This is more than 100 times better than steel. This is the vibration damping capacity, and 2000 times better than aluminum, for example. If you compare cast iron with the steel or the aluminum, you can see that this is 100 times better in terms of the vibration damping. Okay. So, it has very good vibration damping capacity. Right. Fatigue resistant. So, fatigue is the repetitive load. So, it can withstand the repetitive load for a longer time than the other materials, than the comparative materials. Machinability is good to bad, in the sense that you know, it is a brittle material. So, it is a hard material, and while machining it will have the discontinuous chips, and therefore, we say that machinability is not very good, but not so bad, okay, like that. Now, usage, engine blocks, cast iron is used widely in making the engine blocks or machine frames. Okay. Next is the steel, where, as I said, that percentage of carbon, if in case of cast iron it is 3 to 4%, in case of steel it is less than 2. Okay. So, therefore, steels are produced by reducing the percentage of carbon, silicon, manganese, phosphorus in the pig iron. Okay. So, pig iron is from the blast furnace. There we have certain composition of the carbon, silicon, manganese, reducing those compositions, and we are getting the steel. That is as simple as possible required. Now, the classification of the steel is there are plain carbon steel, there are alloy steels. Okay. Plain carbon steels, they have in the under the plain carbon steel we have the low carbon steel, where we have the percentage of carbon less than 0.3%. Okay. Then we have the medium carbon steel. Medium carbon steel is little more than the low carbon steel carbon content, and it is between 0.3 and 0.8. So, you understand that the medium carbon steels have the different grades depending on the percentage of carbon. In some grades it may be 0.3, then 0.4, 0.5 and so on, but not more than 0.8% of the carbon. High carbon steel, there the percentage of carbon is more than 0.8%. Okay. Now, the small amounts of other elements apart from the carbon, like 0.4% of manganese, okay, 0.05% of sulfur, 0.04% of phosphorus. So, these are the materials which are added along with the carbon in this percentage. You can understand that this is a very small percentage in comparison to what we have seen in case of the cast iron. Okay. Now, more the carbon content, hardness will be more, like in the case of the cast iron for example, but less will be the ductility. Okay. This is the contradiction between the carbon content, ductility, hardness and so on. Lowest cost steels are the plain carbon steel. Amongst all the other steels, plain carbon steels are of the lowest cost. Form the major proportion of the steel produced. These are the plain carbon steel, because this is cheaper and it is easier to form, easier to manufacture. Okay. So, therefore, it forms the plain carbon steels form the major proportion of the steel that are produced in the industry, metallurgy industry. Now, alloy steels, by definition, alloy of iron and the carbon containing a high amount of alloying element other than elements in the carbon steel. Now, in carbon steel we have seen that there are alloying elements like manganese, sulfur, phosphorus. In the case of the alloy steels, there are high amount of alloying element other than elements in the carbon steel. Okay. First of all, those elements will also be there, manganese, sulfur, phosphorus, their percentage can be more, and there are many other elements which will be used as alloying material, okay, or alloying element. Now, the properties of the alloy steels are that they give better strength, okay, ductility and toughness compared to plain carbon steel. That is one thing. This is a major contribution of the alloy steels, and the demand in the engineering fields, as you understand, that the strength has to be more, ductility should be there, because that will help in the machining, in forming the material. So, those are the demands from the engineering, and therefore, the alloy steels came into picture, came into market, since the plain carbon steel and the any carbon steels, be it a medium carbon steel or high carbon steel, they were not satisfying these demands of strength, ductility and toughness. Okay. So, therefore, the alloy steels are being started used in the engineering practice very widely. However, as you understand that the alloy steels will be costlier than the carbon steels, obviously. Now, effect of alloying elements, if you see, manganese, for example, manganese improves strength and hardness of the material. Chromium improves corrosion resistance, strength, wear resistance and the hot hardness. Well, you understand what is corrosion resistance, strength, wear resistance. Hot hardness is something which is different from the hardness, in the sense that it is at high temperature, elevated temperature, when the hardness is not lost, hardness is material is keeping the hardness at elevated temperature, that is the hot hardness. We say that material has more hot hardness when it can maintain its hardness at elevated temperature, that is called the hot hardness property. Next is the nickel improves strength, toughness. Okay. that is to withstand the vibration, for example, or shock loads, for example, and so on. Molybdenum, for example, increases tensile and creep strength at high temperature. Okay. Now, of course, these are all given, these effects are given qualitatively, but you have to understand that manganese improves strength and hardness within certain level. So, you have to, that research went in the alloying material and it is still continuing in the alloying material field by changing the composition, by changing the percentage of these alloying materials and the combination of the alloying materials, different properties can be obtained. Okay. So, although it is given just qualitatively, but we have to find out how much exactly will improve the certain property, okay, by what extent, that is important. Now, the types of alloy steels are there are stainless steel. Stainless steel, everybody knows that nowadays it is very useful and very widely used. Large family of steel containing at least 11.5% of chromium. Okay. This is one major alloying material in the stainless steel. Corrosion resistance due to the formation of this chromium oxide, because there is chromium. So, therefore, it does not allow the corrosion since the chromium oxide is formed. Okay. Most stainless steels show good short time strength up to 1100 degree centigrade. Okay. So, it is a very high temperature, by the way, and even at that high temperature it will have the strength, it will retain the strength for a short time, and after this is increased, temperature is increased, the strength will be less compared to plain carbon steel, which lose their usefulness above 510 degree centigrade. So, you can see the effect of the alloying materials, that if we are, it is the same, see, steel and adding some very small percentage of alloying material, what we are doing is that in case of plain carbon steel, they cannot withstand more than 510 degree centigrade, because they lose their strength. And in this case, the alloying material, stainless steel for example, it can withstand even 1100 degree centigrade. So, almost twice of that, okay, more than twice of that. Now, the next property is that the thermal conductivity of stainless steels are poor. Okay. Copper cladding, therefore, is often used in cooking utensils for distributing the heat. So, you must have seen the utensils, stainless steel utensils with the copper coating below, okay, at the bottom. So, that is for distribution, equal or homogeneous distribution of the heat, because the stainless steel will since it is not a good conductor of the heat, thermal conductivity is not very good. Tool steels, these by name itself it is meant that the steels are used to make the tools, different kind of tools. Okay. Tools for the conventional cutting process, single point cutting tool, milling cutter, drills, okay, and also for the metal forming operations, dies, punches, and so on. Now, tool steels contain elements such as carbon is about up to 1.3%. So, it is 0.8 to 1.3%, manganese up to 1.6%, starting from 0.2. So, it is 0.2 to 1.6% of manganese, chromium, okay. Then the wolfram, that is the tungsten. Okay. So, W came from the Latin word wolfram. Wolfram is the actual meaning of this tungsten. In English it is tungsten. So, therefore, it is W, but otherwise you can see that chromium is like CRO. So, it is CR, vanadium VA, molybdenum is MO, okay, and then cobalt is CO, but this is the wolfram. So, this is the tungsten. Now, as you again understand, I will just repeat once more that this is a range. Okay. So, depending on the exact carbon content and depending on the exact manganese percentage, for example, you can have different properties in the tool steels. So, tool steels grades can be different depending on the percentage of carbon within 0.8 and 1.3%, the percentage of manganese within 0.2 to 1.6% and so on. Now, these percentages of chromium, tungsten, vanadium, molybdenum and the cobalt, these percentages are very small. So, therefore, they are not really mentioned. It is about, for example, in some of them it is 1%, some of them, well, 1% is higher rather, because it is almost comparable with this. In some places it is about 0.6% and so on. Now, the other properties are the class of high carbon alloy steels, that is both shock and the wear resistant. Now, tool steels, this is is a modification, that is another class of the this high carbon steel, alloy steel. Okay. And it has both shock and the wear resistant, it can withstand the shock. Okay. Now, where we need that shock resistant in the tool steel? Now, it is, you understand that when the say if we have a turning tool, okay, the single point cutting tool, and it is used, it is fabricated out of the tool steel. So, in case of inhomogeneous hardness in the workpiece, which may happen because of the hard particles inclusion inside the workpiece. So, whenever the tool is cutting going through the material, and because of the inhomogeneous hardness, there will be different kind of work, I mean the forces will fluctuate. Okay. So, because of that fluctuation, there will be some shock to the tool. Okay. So, that has to be withstood, and this kind of tool steels, which is another class of the high carbon alloy steel, as it is written, as I told you, it has this property, as well as it can actually resist wear to a large extent. Okay. Withstand high temperatures, and withstand high temperature, particularly that it retains its hardness with the elevated temperature, at an elevated temperature, higher temperature. Steel for electrical and magnetic applications. So, those compositions will be different, because the demands from those steels in the area of electrical and the magnetic applications will be different. Now, those kind of steels you are may have the 0.5 to 5% of silicon. Okay. That increases the electrical conductivity, because we need it for electrical usage application, and permeability. Okay. So, because of that, these two properties, that the conductivity and permeability, the which is given by the silicon. So, percentage can be varied from 0.5 to 5%, depending on again exact percentage of silicon. You will have the different grades and levels of the permeability or the electrical conductivity. Such kind of steels are used in electrical motor generators. For example, when the the binding, the wire which is required for making the bindings, okay, and the transformers. Okay. In transformers and the motors, apart from the housing, apart from the structure and the wire that is required, all these material can be this kind of materials with the silicon percentage up to 5%. Reduces power loss associated with the heat problems. Okay. Meaning that these steels are specially made so that at high current and the high voltage, the temperature which is produced, there the power loss should not be there. That in the case of transmission is very important thing, and so that the output could be according to the input that is given, okay, in the generators or the motors, okay, and transformers. Let us discuss some of the non-ferrous metals, and let us see how they differ from the ferrous materials in terms of properties, in terms of usage and so on. Let us say first representative of the non-ferrous material is of course aluminum, which is very widely used, and as you understand that this is a light material. This is a cheaper, relatively cheaper material. Of course, it is not so cheaper than, not as cheap as, not cheaper than the steel and so on, but nevertheless it aluminum predominantly used in the aerospace industry, because it is light, as I said, and 80% weight by commercial aircraft, in the commercial aircraft, this is borne by the aluminum parts, the parts made of aluminum. Aluminum and the alloys, of course, it is not pure aluminum, as you understand, the entire housing, for example, okay, and so on. This is in the form of aluminum or aluminum alloy. I am coming to that aluminum alloy, which will give you different properties of the aluminum. Aluminum has emerged as a valuable source of metal for the automobile industry, again because of the lightweight, because of the sufficient strength. Okay. Of course, it is again the aluminum alloy mostly, not the pure aluminum, and because of these properties, in the automobile industry it is very popular, as you understand. And basic thing is that when the automobile is becoming lighter, it will actually consume less power. So, therefore, it will consume less fuel, and that is very important. And if we are gaining gaining in the weight of the automobile, this is a drastic reduction in the power and drastic reduction in the fuel consumption can be achieved, which actually are being such automobiles are being designed these days, and which you can see on the roads these days. Properties of aluminum and aluminum alloys. So, high strength to weight ratio. Okay. The ratio of the strength to weight is very high. So, you understand that for less weight with very high strength can be achieved. So, therefore, that strength to weight ratio can be very high. Ease of machining and forming, because it is relatively softer material. Okay. So, therefore, the machinability is good, and for formability is better. So, using the metal forming, you can have the different kind of material, different kind of parts. Using the casting, as you understand, of the aluminum, you can have different kind of parts. So, after casting, it can be actually machined easily if it is required. Similarly, after forming, it can be given a finish shape if it is required. So, that case machinability of the aluminum will be better, and it is very desired property, because in many cases after the casting, after the metal forming out of aluminum material, we need to have the final shape by machining. Next property is the resistance to atmospheric corrosion and attack by certain chemicals. Okay. You understand that this is when we are talking about the aluminum always will have a very quick formation of the aluminum oxide layer, and that aluminum oxide layer, like in the case of the cast iron that we have discussed earlier, it will actually serve as a protecting layer on the top of the workpiece, and therefore, we are saying that the resistance to atmospheric corrosion, particularly atmospheric corrosion resistance high for the aluminum alloys. Okay. Pure aluminum, of course, will have a quick formation of the aluminum oxide on top of it, which is harder, and attack by certain chemicals, not all, but certain chemicals. Aluminum and aluminum alloys have the high electrical conductivity, okay, and for that, in the electrical wires also, you can see that there are a huge number of aluminum parts and aluminum material, aluminum and aluminum alloys, they are used. Now, aluminum lithium alloys, for example, each percentage of lithium, by the way, up to 4%, reduces weight by 3% and increases stiffness by 6%. This is the experimental results, and you can see the effect. Each percent, okay, up to 4%, reduces weight by 3%. This is drastic reduction in the weight, by the way, and increases the stiffness by 6%. Okay. So, both these characteristics like the weight and the increased stiffness, they are desirable in the engineering materials and for the engineering parts. So, therefore, the role of lithium is great in case of the aluminum alloy, that has been found out by research. Greater fatigue resistance. Okay. So, repetitive loads can be withstood by such alloys, aluminum lithium alloys. It will reduce weight of commercial aircraft by 10 to 15%. Look at that, 10 to 15% reduction in the commercial aircraft means it is a huge reduction, and the huge reduction not only in the weight, but subsequently in the power consumption. Okay. So, power consumption means the fuel consumption, less fuel will be consumed, and you understand that in the aircrafts the fuel is very expensive because very high quality fuel is used, and if the weight is reduced, power is reduced and the fuel consumption is reduced, it is a great achievement for the aircraft industries. Titanium, properties between those of steel and aluminum. So, you understand that this is all the properties that the steel have and the aluminum have, the properties of the titanium will be in between. We will tell in details what are those. Strong, lightweight, corrosion resistance. These are the three properties which are also very important for the engineering field of engineering materials. You understand that, because they have to be stronger, strong material, weight has to be lighter, and it cannot have the corrosion. This should have the corrosion resistance. Corrosion, otherwise it will be actually in the long term, the part will be destroyed. You understand that it goes into the material and it destroys the part, it reduces the strength and finally it can actually break. Mechanical properties are retained up to 535 degree centigrade, particularly the hardness. So, the hot hardness is reasonably high. I would not say that this is very high, because 535 degree centigrade is not so much high temperature, but still at this temperature the properties including the hardness are retained for the titanium parts, for which the titanium material is widely used in engineering. Problems with titanium is that chemically very active particularly in the molten state. Okay. So, when it is being produced, when it is being melted, or it is melted for other purposes, for example casting or for getting the powders and so on, they are chemically very active. It can react chemically with the atmosphere or the other gases and so on, absorbing oxygen particularly and nitrogen from air with ruinous capacity. So, in the molten state particularly, it can absorb oxygen and nitrogen from the air to such extent that it can actually ruin itself. The properties of the titanium can be ruined because of this absorbed oxygen and nitrogen. Difficult and costly to produce. So, therefore, the titanium material is kind of very rare and it is very expensive. Okay. High temperature metals and alloys, jet engines, gas turbines, rocket and nuclear applications, they require the materials with high strength, creep resistance, okay, corrosion resistance. This is understood, because these are mostly they are working at a very high temperature. That is one thing, very high speed. So, therefore, the forces exerted will also be higher, temperature rise will be high. So, therefore, for all this it needs the corrosion resistance, creep resistance and the high strength of the material. At temperatures in excess of 1100 degrees centigrade. So, the temperature may go of course more than 1100 degrees centigrade. So, at this temperature all these properties should be retained, that is high strength, creep resistance and corrosion resistance. See, the important point for these parts or this material for the jet engine, gas turbine and so on, it is not only the overall properties, but we always ask that these properties should be retained at higher temperature, because mostly in the jet engines, gas turbines, rockets, nuclear applications, the temperature goes beyond this 1100 degree centigrade. All right. So, at that high temperature, when these properties are retained, that is valued and that is desired. Okay. Future jet engine temperatures may well be above 1400 degree centigrade, because the speed is increased and therefore, the temperature is increased and the forces exerted on them also are increasing. Okay. Therefore, materials like super alloys are invented. Nickel, ferrous, titanium and cobalt form the base of these materials. These are the super alloys formed by nickel, ferrous, titanium and cobalt. In aerospace particularly, the titanium based super alloys, for example, aluminum made of aluminum, carbon, molybdenum, vanadium along with the titanium. Okay. Titanium will be the base. That is very widely used in the aerospace, particularly because they become very light, okay, and strength wise also it is sufficient for the parts made in the aerospace industry. Turbine blades are mostly nickel based along with the ferrous and the chromium. So, these are the super alloys which will have superior properties that are required and used in the aerospace or the aerospace industries particularly, because turbines mostly are used in the aircrafts, all the motor engines, you understand that, and there the super alloys are used for making the blades, making the housing and so on. Refractory metals, niobium, I suppose this is 2470 degree centigrade, it can actually withstand. Molybdenum can withstand 2610 degree centigrade. Tantalum can withstand even more, up to 3000 degree centigrade, or tungsten can withstand 3410 degree centigrade. So, the refractory metals, you know that those metals are used for making the layers in the furnace, okay, in the where you melt, we get the molten material. We prepare the steel, alloys, alloying materials, okay, alloy steels and so on. So, there the temperature becomes very high and we cannot have any loss in the temperature. So, therefore, inside those furnaces there is a layer which is made by the refractory metals, and the refractory metals therefore should withstand very high temperature, and you can see that these materials actually can withstand really high temperature, which is beyond the melting temperature of many metals actually. Ceramics, compounds of metallic and non-metallic elements, these are the ceramics, often in the form of oxides, carbides and nitrides. Okay. So, there are different kind of oxides, different kind of carbides, we will see this, and the nitrides which are actually the ceramics, which are called the ceramics. Now, the characteristics of the ceramic are that they have very high melting point. Melting point is more than 1500 degree centigrade. So, therefore, at very high temperature like up to this temperature it cannot melt. Okay. Compressive strength can be 5 to 10 times of the tensile strength. Okay. Here as you understand that these materials are the brittle materials, ceramics. Okay. So, therefore, their tensile strength is not high, but the compressive strength is very high. This is even 10 up to 10 times more than the tensile strength. Because of that property, actually because of the high compressive strength, these ceramics are very often used widely. Very brittle and lack of ductility. Okay. Some ceramics like silicon carbide, silicon nitride, they offer moderate toughness. They can reasonably well withstand the shocks. Okay. Now, ceramics are overall not very good shock absorbers. If you have a let us say for example, in case of tools, in case of tools in machining, the tools are made of ceramics, but those tools cannot withstand the vibration in the machine tool. Okay. If the tool vibrates, then the ceramic tools actually can break. All right. So, therefore, in case of turning tools, the ceramic tools are made fatter, so that they can actually withstand the high fluctuation of force particularly. Okay, that is not very good for ceramics. Young's modulus higher than the steel, very stiff and considerably harder. Okay. Especially useful as wear resistant parts and for abrasives, like very often ceramic particles are used in terms of silicon carbide, for example. Okay. So, we said that silicon carbide, silicon nitride, they have the moderate toughness. Okay. So, those silicon carbide particles are also used as the grinding wheel grits. Okay. So, that we will discuss when we will discuss the machining part in the conventional machining, that grinding wheels are very widely used the abrasives. Okay. This kind of abrasives like ceramics. So, particularly the silicon carbide. Cutting tools, very often cutting tools are of the tungsten carbide. They are very strong and they cannot withstand, of course, they are brittle as I said, but they can withstand very high temperature and they have the quite a good wear resistance. All right. So, the tools do not wear out very easily when they are made of the tungsten carbide. Tungsten carbide is a co-bonded, okay, with the tungsten carbide. Applications: silicon carbide and silicon nitride work well in high stress, when the stress is high, high temperature applications such as turbine blades. So, blades are made of along with the silicon nitride and the silicon carbide as well. May replace nickel or cobalt based superalloys, because the properties of these ceramics will be closer to those superalloys, nickel or cobalt based superalloys. Silicon nitride, for example, is 1/2 the weight of the stainless steel. Okay. So, you can understand that these are much lighter materials also. So, if you are using the stainless steel, the structure will be much heavier than the use of the silicon nitride. But in case of silicon nitride, of course, it is more expensive than the stainless steel, but where you have the weight as a factor, in that case you have to you cannot compromise with the property and you have to go for the high cost of the silicon nitride. Okay. Sialone, for example, this is a relatively new material, and I will just tell you the definition of that. The sialones are ceramics based on the elements silicon, aluminum, oxygen and nitrogen. That is why the name came, silicon, aluminum, oxygen and nitrogen. Okay. So, sialone. They are solid solutions of silicon nitride Si3N4, where silicon nitrogen bonds are partly replaced with the aluminum nitrogen and aluminum oxygen bonds. This is how the sialone has been invented. Okay, that silicon nitride, these bonds, they are partly replaced by the aluminum nitride, aluminum nitrogen and the aluminum oxygen bonds. Okay. Now, they have good resistance to wear and thermal shock. Okay. It is stronger than steel, by the way, extremely hard and light as aluminum. So, you could see the extremely good properties, like stronger than steel, okay, extremely hard, light as aluminum. So, that meaning that it is using the all the good properties of the steel, aluminum materials. So, good resistance to wear and thermal shock, as I said. It has the good electrical bad conductor, so it can be used as an insulator. Okay. Retains good tensile and compressive strength, particularly up to temperature of 1400 degree centigrade. It is a very high temperature, you can see that, and it at that temperature it may have the tensile and the compressive strength retain. Okay. Ceramics engine blocks are also coming up. Okay. So, that is ceramic material is used for making the engine blocks as well. Refractory materials in furnaces and high temperature reactors. They are used because they can actually withstand very high temperature, they can retain good tensile and compressive strength. So, therefore, in the engine blocks, in the refractory materials, in furnaces. Okay. So, they are used as this kind of material. So, in engine blocks, of course, it is a layer, it is not full engine block material, could not be from the ceramics. Okay. So, it is a layer inside the engine block which is of the sialon material, it is also ceramic material. Heating elements for furnaces, for example, silicon carbide. Okay. Substitutes for joints, bones, dental implants. This material is now being more and more popularly used in the dental implants and the substitute for the joints. Okay. Now, composite materials, as I was telling you that this is these are the materials which have lately started being used very extensively because of their unique properties, particularly they are light and strong. Okay. And they are relatively less expensive, they can be made, produced easily and so on, relatively easily. Heterogeneous solid consisting of two or more different materials that are mechanically or metallurgically bonded, these are the composite materials. Once again, these are the heterogeneous solid. Okay. And they consist of the two or more different materials that are mechanically or metallurgically bonded. We will see how they, what does it mean that mechanically and what does it mean metallurgical bond. Advantages of the composite materials are that they can combine conflicting properties such as ductility, strength and hardness, resulting in a new material with a unique combination of low weight, stiffness, strength and creep resistance, corrosion resistance, hardness and conductivity. You can see that in case of the material, if you have a hard material, normally they are brittle. Okay. So, if you have the strength, high strength, though they may not have the ductility. If you have high hardness, they will not have the ductility and so on. So, in case of composite material, this is the advantage that it can combine these conflicting properties. Okay. It can have the ductility as well as the hardness, for example. These are the unique properties which are desired in the engineering materials, okay, to make the engineering parts which needs very high hardness, and they should be also ductile to a certain extent. I will give you examples in the course of our discussion that we need to have the parts, we need to have the tools even which will have the hardness as well as the bit of ductility. Okay. Now, as I said that they are these composite materials, therefore, are of low weight, stiffness, strength and creep resistance high, corrosion resistance is high, high hardness and high conductivity. Okay. Now, the classification in the composite materials are that laminar, it may be laminar or layer composites as it is said. For example, plywood, they have the layers of wood bonded together with their grain orientations at different angles. Okay. So, this is called the plywood, this is also a kind of a composite material, all right. Improves strength that way because it has the grain orientation, depending on the grain orientation they are actually those grain orientations are at different angles. So, therefore, depending on that you can actually gain the particular strength, you can obtain the particular strength, and the fracture resistance. It cannot actually fracture very easily, all right. Reduces swelling and the shrinkage. So, this is very important, particularly for the household doors and windows, as you understand that under the rain, okay, they should not swell or they should not shrink at a higher temperature or at when the humidity is less, for example, the dry condition, they should not shrink. In that case, you understand that the doors and windows and all household furnitures and all, they will suffer. So, this is the plywood, which is also a kind of a composite material. Safety glasses, windshields for example, okay, adhesive layer placed between two pieces of glass. So, this is how the safety glasses or the windshields are made, all right, because they have the adhesive layer. So, they cannot actually break in pieces, but they retains the fragments when the glass is broken. This is important. You might have seen that if a stone falls at the windshield of an automobile, it does not actually come out, okay, it does not break into pieces, it actually breaks and stays there, the pieces can stay there, all right. So, this is done by the adhesive layer placed between the two pieces of glass. This is how the safety glasses are made. So, this is also a kind of a composite material, okay, as per the definition. Particulate composites are there. Particulate composites are the discrete particles of one material surrounded by matrix. Okay. Common example is a concrete. It is a discrete particle of one material. Which material? It is a cement for example, surrounded by matrix. Okay. So, this can be the cement and the granules, okay, that makes it, and the sand for example. So, that will be the concrete. Hard particles, soft matrix. Okay. So, pronouns strengthening, better creep resistance, toughness, all right. Examples, they are the cemented carbides that are used as tool, for example, tungsten carbide, tantalum carbide, titanium carbide, okay, dispersed in metal matrix. So, these are the cemented carbides, as you may remember that these are the materials also they are used for making the tools, okay, cutting tools. Generally that metal matrix used there is the cobalt. Okay. So, the cobalt metal matrix and the powders will be tungsten carbide, tantalum carbide and the titanium carbide, all right. As a result, you will get the unique properties that we have discussed. High strong material, it can withstand the shock loads, okay, it can withstand the fatigue and so on. Hard stiff carbides can withstand high cutting temperatures, that is very important, but extremely brittle. Okay. Toughness imparted by the cobalt matrix. So, cobalt matrix improves that shock absorption property to an extent, all right. Properties also depend on the size of the particles, of course, volume fraction of particles, that means how much, which particles are in which volume in the what is the fraction of this volume, okay, fraction of those particles in that volume, and the mechanical properties of the particles and the matrix both. Okay. So, in the composite material, the properties of these particles or the matrix may not be retained, okay, the properties may not be may be different, and the properties normally are better than the properties of the particles and the matrix taken individually. Okay. It is like case of the mixture when you are making two liquids also. So, it happens, you know that, and therefore, in the composite material the properties that you are getting will be unique, and this is different, it may be different from those particles and the matrix, but it will depend on the size of the particles, volume fraction of particles. You understand that if there are smaller particles for example, it will actually can withstand, it is better than in case of the particles which are larger in size, because the density is more, and therefore, it will be stronger and so on. So, volume fraction of particles has the same kind of an explanation why the properties can be better if the volume fraction of particles is more, but not in all cases, it depends. Okay. So, the rest of the things in the composite materials we will be discussing in our next discussion session. Thank you for your attention.